All right, break time is over. We're going to resume class. Before class, we were talking about operation of two-level memory. That means that we needed to export the locality. The upper level memory, that is M1, need to be smaller and faster, but a bit expensive. That means that the M1 temporarily stored a part of M2 is content, because on memory reference, the system first check for M1 is content for item. If it is found, that means it is a hit. If it's not found, a block from the M2 needs to be copied to M1. This means the access will be done via M1. So locality makes sure that multiple accesses to the block is in M1, which will improve the speed of the memory system as well as the speed of the computer system. So we need to talk about the average access time for a two-level memory. The average access time, that depends on both level 1 memory and the level 2 memory. That is M1 and M2 in our case. So the probability that a reference is found in M1, we call it a hit rate. We just talked about this before break. Now we needed to find the TS, which is the average access time for this two-level memory, which is equals to H times T1, H which is the hit iteration, that is the fraction of the time reference is found in M1. Then we have the T1, which is the access time of M1 level, then plus 1 minus the hit iteration times T1 which is the access time of M1, and plus T2 which is the access time for M2. It also equals to T plus 1 minus H times T2. That is H times T1 plus 1 minus H times T1 plus 1 minus H times T2. Now, here we have T1 plus 1 minus H T2. That is, we have T1 plus 1 minus H T2. We have the average access time, which is also equals to the time of accessing the item from M1 plus 1 minus the iteration. That is the fraction of references is found in M1 minus the iteration times T2. So this is the expression of finding the average access time, which it depends on the speed of both memory, the memory in level 1 and the level 2. That is M1 and M2. Next, we have performance of accessing, which involve only level 1 memory, that is the iteration. Now, here we have on x-axis, we have fractions of accesses which involve only level 1, that is the iteration. Then on y-axis, we have average access time. That means that if you try to see with higher H value, that is higher fraction of accessing, which involve only a level 1 memory, this will make average access time closer to T1 than T2. Now, this is clear. If you try to analyze this picture here on the screen, with a higher H, here we have a higher H, which is 1. That means the average access time is approaching T1. The average access time is approaching T1. So that means that with higher fraction of accesses which involve only level 1 memory, we have the average time which is closer to T1. High values of H makes the average access time closer to the T1. That is the time that requires the CPU to fetch data, the item from M1 level. Now, the performance has to be improved significantly when level 1 hits are frequent. If we have most of the data items stored in level 1 cache, that means we have the performance of the computer system that needs to be improved, as we have many data items in level 1 cache. So average access time in level 2 cache memory depends mainly on heat duration, that is H. That is the fraction of the memory access found in faster memory. So this picture clearly depicts that with higher H value, this will make average access time closer to T1. The T1, which is the time that the CPU requires to retrieve data from level 1 cache. Now we have this picture which mainly depicts the performance of accessing, which involve only level 1 memory. We have a fraction of accesses which improve only level 1 cache with higher levels of data found in higher level memory. That means the average access time will be less. The average access time will be closer to T1, which is the average access time that the CPU requires to retrieve data from level 1 cache. Now, we needed to talk about average cost per bit as well. We just talked about average access time, but we also needed to talk about what is the average cost per bit. Now, we needed to have a look at some other parameters as well, which can help us to access a level 2 memory mechanism, considering the cost. Now, considering the cost, if we consider the cost, we have to assess the memory average cost per bit. Average cost per bit for a combined 2-level memory is given by this expression. Average cost for a combined 2-level memory per bit is C1, which is the average cost per bit for upper level memory, that is level 1 memory, times S1, the S1, which is the size of the level 1 memory, plus the cost C2, which is the average cost per bit of lower level memory M2, times the size of level 2 memory, divided by the size of level 1 memory times the size of level 2 memory. Now, we have this average cost per bit for a two-level memory. We have the average cost per bit for the combined two-level memory. We have the cost for a bit of the upper level memory. That is for level 1 memory, M1, times the size for level 1 memory, that is M1, plus the average cost per bit for level 2 memory, that is M2, divided by S1 which is the size of the memory, plus S2 which is the size of M2. So we would like to get average cost per bit for the combined two-level memory, which is approximately the cost for the average cost per bit of the lower level memory, which is the lower level M2. Now, given that the cost of the level 1 memory, it is extremely greater than the cost of the level 2 memory, this requires the size of the level 1 needed to be less than level 2 size memory. So it is clearly understood that the cost per bit, average cost per bit of the combined memory is equals to the average cost for the memory level 1 times the size of the level 1 memory plus the average cost for the size for memory 2 times the size for level 2 memory divides the size of the level 1 memory plus the level 2 memory. So we are looking for the average cost of the combined two-level memory to be equals to the average cost per bit of the level 2 memory. So given that the level 2 memory cost is less than the level 1 memory, we want the size of memory level 1 memory to be less than the size level 2 memory. So we are looking for average cost per bit for the combined level 2 memory to be equals to average per bit for level 2 memory. But since we have the cost of level 1 memory, which is greater than the cost per bit of the level memory, then we need to minimize the size for level 1 memory so that we get the cost per bit of these two combined memory to be almost the same. Now, this picture on the screen, it does depict a relationship average memory cost to the relative size of a two-level memory. On x-axis, we have relative size of two-level memory, that is S1, S2 divided by S1, and on the other side, y-axis, we have relative combined cost, that is average cost per bit of the combined memory divide average cost per bit for level 2 memory. Now, as I said, we would like to get the average cost per bit for the combined memory to be equals to the average cost for the level 2 memory. So, given that the cost of average cost per bit for the level 1 memory, C1, is greater to the average cost per bit for level 1 memory, this requires that the size of the level 1 memory needs to be less than the size of level 2 memory. This figure shows this relationship in more details. Now here we have relative size of these two-level memory, and here we have the relative combined cost, and we see that since we are looking for the average cost for the combined memory to be equals to average cost per bit for the level 2 memory, and since we know that the cost per bit for the level 1 memory has to be greater to the average cost per bit for the level 2 memory. We want the size of level 1 memory to be less to the size of level 2 memory, so that we get the average cost per bit for the combined two-level memory to be equals to the average cost per bit for the level 2 memory. Again, when it comes to memory performance improvement, we know that the average cost for the combined average access time for the combined two-level two memory system, we have the heat relation times the time to get access to the item in level 1 memory plus 1 minus h, which is the rate iteration, times T1 plus T2. It is also equals to the time used to get access to the item in level 1 memory plus 1 minus the heat iteration times T2, as I have also demonstrate on the board. We need a two-level memory to provide a significant improvement. So we need the average access time for the combined system, for the overall system, to be approximately the T1. So to get the average access time to be approximately equals to the time T1, that is the CPU we use to fetch the item from the level 1 memory. So given that T1 is much less than T2, that means the T1 is less than T2, we have a heat relation that needed to be close to 1 is needed. So to make Ts equals to now to make Ts now what can we do to make a Ts equals to T1? To do so, we need a heat iteration here, which has to be equals or closer to 1. That means the average access time will be approximately equals to the time T1. So this is very important to understand that we need a two-level memory to provide a significant memory performance improvement. So we need the average access time, Ts, to be approximately equals to the T1. So given that T1 is less than T2, that means we have a heat iteration which is closer to T1, and it needs to be done. So we would like to get M1 to be small, to be small in terms of downing down the cost, and large to improve the heat relation. Therefore, the performance has to be improved. So is there any size of M1 that needed to satisfy this requirement for a reasonable extent? This is the main question. So we needed to answer this question with a series of sub-questions. Now, what vary of heat relation? Now, this is the main question. What vary of heat relation equals to what? To make Ts equals to T1. Which value of heat relation will be satisfy this condition? This is the main question. The next question is, what size of M1 will assure the needed heat relation? Now, what size of M1 to make sure that we have this heat relation? Now, the size that we just found, this we satisfy the cost requirement. There is also a cost requirement that needs to be satisfied. So, we have to get T1 to be approximately equal to the average access time Ts, but given that T1 is much less than T2, so we need a heat relation to be closer to 1, so that the second expression in the expression of the T average access time will be 0. So we need the heat relation, which is closer to 1. So we'd like to get the size of the M1, that is the size of level 1 a cache, to be smaller, to hold down the cost. And we have also to make it larger to improve its heat relation, therefore to satisfy the condition. But is there any size of M1 that needs to be adjusted to satisfy both requirements to a reasonable extent? So we have these sub-serious questions. What value of heat relations is needed? Second, what size of M1 is needed so that we have the average access time equals to T1? So what size of M1 needs to be, to accommodate this heat relation? Now, if we found the size for M1, we need also to evaluate, does the size satisfy the cost requirement? So those three questions needed to be answered. Now, we need to get at this point, we needed to consider the quantity T1 divided by Ts, which is referred as access efficiency. It is a measure of how close average access time Ts is to M1 access time T1. So from the previous equation, from the previous expression, we will get T1 divided by Ts equals 1 divided by 1 plus 1 minus the heat relation times T2 divided by T1. So this is the expression. We have get this access efficiency by using this expression, T1 divided by Ts equals to 1 divided by 1 plus 1 minus iteration times T2 divided by T1. Then this is what we call access efficiency. We call it access efficiency. This we make average access time Ts closer to M1 is access, which is T1. This we make average access time Ts closer to the average access time of M1, that is the T1. So this expression will help us to found Ts, which is approximately equals to T1. T1, which is the average access time, to get the item which is stored in M1. M1, which is the level 1 of the two-level memory. Now, for access efficiency, we need to have this picture on the screen, which helps us to depict that a heat relation in the range of near 0.9 would seem to be needed to satisfy the performance requirement. Now, if you try to see here, if you have a heat relation which is in the range near 0.9, we have to satisfy the performance requirement that we're looking for, the Ts, which needs to be approximately equals to T1, which is the access time for M1 level memory. So a heat relation is in the range of near 0.9 would seem to be needed to satisfy the performance requirement. That means we needed to get this access efficiency as a function of heat relation. This is R equals T2 divided by, this is R equals to T2 divided by T1. This is what we call access efficiency as a function of the heat relation. Here's a picture on the screen depicts that a heat relation in the range near 0.9 would seem to be needed to satisfy the performance requirement. Now, let's talk about heat relation as a function of a relative memory size. Now, we have a relative memory size here, and we have the heat relation. As you can see, if you don't have locality, you see that you have a lower heat relation. As we have a moderate locality, we have also a moderate heat relation. If you have a strong locality, you see that we have a strong heat relation. So that means the heat relation also depends on the principle of locality that we did discuss last time. So with a strong locality, that means a strong locality allows a high heat relation with small upper level of memory. So this picture on the screen depicts that a strong locality allows a high heat relations even with a small upper level memory. So studies shows that cache level memory can achieve a heat relation above 0.75 regardless the main memory size. Now, this picture on the screen depicts that a strong locality provide a high iterations even when we have small upper level memory. So we have studies which depict that small cache memory can even achieve a iteration which is above 0.75 regardless the size of the main memory. Typically, we have the cache size, which is between 1 KB and 128. For the main memory, we have the size of the main memory in terms of gigabytes. So that means that with a strong locality, our cache memory can have a higher performance regardless the size of the main memory. Now, we have also virtual memory and disk memory, which can also help us to confirm that small memory like M1 can also still yield a higher iterations because of the locality. We talked about principle of locality, spatial locality, temporal locality. So we have seen that studies also depict that the virtual memory and the disk caches can also achieve a higher hit rate, a higher iteration, regardless the size of the main memory. So average cost per bit approaches that a cheaper, lower level memory also is needed. So average cost per bit approach that of a cheaper, lower level memory. Now here, this picture on the screen depicts that we have a iteration which is a function of a relative memory size. With no locality, we have lower iteration. With a moderate locality, we have a iteration which has been improved due to this locality. But with a strong locality, we see that there is also a improvement in iteration, even when we have small upper level memory. Now, we just talked about performance of two-level memory. It's better if we can approach the performance of the memory with multi-level memory accesses. So the following sections, we are going to develop a model which can help us to have a clear understanding about the performance in a memory hierarchy that has more than two levels. What we just seen is the memory performance in two-level memory performance. Now we need to extend this memory performance in a higher memory hierarchy. Now we have this terminology that we need to be used in the multi-level memory access. We have M1, MI, which is the memory level at level I. We have also the size. This is the capacity of the level MI. We have also TI, which is the total access time needed to get data from MI level memory. Now, is the sum of all the times in the path of a hit in the level MI, or maybe an average? So we have also iteration at any level MI memory. This is what we call the conditional probability of that the data for a memory access is in level MI, given that is not in MI minus 1. That is the upper level memory. Now we have TS, which is the mean time needed to access the data. Now we're gonna develop a memory performance considering memory hierarchy. What we just done was about only memory performance considering level 2 memory. These are the terminologies that we need to be used. We have MI, which is the memory level. We have the SI, which is the size. We have the TI, which is the total time needed to access data in level MI. We have also the iteration, HI. We have also the TS, which is the mean time needed to access data. Now, we have the TS, which is the average access time across all the memory levels. We have higher iterations at each level, which reduce the average access time across all memory levels. Now, EDR, we have the hit lesion in level 1 memory equals to 1. That means this will make the average access time to access data across all memory levels equals to the T1. T1, which is the access time to get data, to retrieve data from level 1 memory. Now, we have this picture on the screen which depicts a multi-level memory access performance model. We have the CPU here, the CPU which needs a block from a memory. We have this comparison. We have a block MI. Now, is the block MI available in M1 memory? If it is available in M1 memory, we have a hit, and the data will be sent to the CPU, and that is done. Now, if the data is not available in M1 memory, there is a miss. That means the CPU did not found the data in M1 memory. So, since it doesn't found the data in M1 memory, it has to fetch in M2. That is level 2 memory. If it is then, the CPU will get access to the M2 memory, and the data will be moved to M1. That is T2, the time to access data from the M2 level. So you see, because of the principle of locality, the data will be accessed from M1. Now, if there is no block in M2, it is a miss. So the CPU will have to fetch the data from another block, the next level memory. That is Mn minus 1. If it is there, it is a hit. Then the data will be moved to the upper level. That is Mn minus 2. And if it's not there, it has to fetch the block from Mn block. And if it is found, that is a hit. Now we need to get access to the data from Mn, and this data will be moved to the Mn minus 1. That is the upper level. So that if there is any next request of the same block, the data will be retrieved from upper level to improve the memory performance. That this will improve your computer performance. Now, if there is no block in any level of the memory, there is a loss. There is a mistake. Is a miss? Is a miss? There is a mistake. So this is the multi-level memory access model. Make sure you do understand that this is very important because it's going to help us also to go into more details about the computer performance. So the previous figure is a simplified memory access model that helps us to deliver the average access time. The step 1, the processor requests a memory address. It has to check if the word is in the level 1, M1, with a probability of hit ration H1. If it is present, it is a hit, and the word needs to be delivered with a time in time T1. Step 2, there are many levels. So for higher levels, M2 up to M1. So if there is a miss in Mi minus 1, that means it has to check the data in next level with a probability of HI. That is the iteration. Now, access time for Mi, that is the TI when it's found. So the process will have to be continued through the memory hierarchy until the word is found. If the word is not found, that means that it is a mistake the data is not available in the memory. Now, if you try to see here, we have the CPU which provides the address of the block, and the block will be set from upper level memories to the lower level memory. And this is, if it's found here in M1, that is a hit, that is the hit, then the data will be accessed through M1. If it's not there, that is a miss. That means that there is no block in M1. The CPU will fetch the data from the next level of the memory. That is M2. If it's found, the data will be moved to the upper level of the memory, and that is done to the CPU. If not, no miss, the data will be found in the next level of the memory, and with this access time, the Tn-1. If it's not there, you have to fetch the data from the next level of the memory, and that is Tn, and so on and so forth. So that is the procedure. That means that the multi-level memory access time, Ts, the average access time for a multi-level memory system, can be expressed as the weighted average of the time of each path. So we have different paths through the picture that we saw in the previous slide. We have different paths. So we have the average access time, Ts, which is equals to the summation of all the paths, probability of taking a path, times the duration that the CPU spent in the path. In other words, we have the summation of all the paths times the probability in the path times all the times in that path. So this is a simplified expression of the average access time, which is a weighted average of the time of each path. Now, here we have the summation from I to n, and we have I minus n, I1 minus hrg, and this is the heat duration times the hr times TL. Well, H0 is assigned to the value 0 in case we have found the upper level. This is the value, this time, in multi-level memory system. Now, if you consider a simple system which consists of only one level memory cache, that is M1, and the main memory M2, and a secondary memory M3, then the average access time is expressed as follows. We have the heat duration in memory level 1 times the time in it is spent in M1 plus 1 minus H1 times H2 times T2. That is the time that the CPU spent in fetching the block in M2, plus 1 minus H2 times H3 times T3. That is the time it spent to fetch the block from M3, the main memory. So in today's class, we mainly focused on memory performance. We went through an example of two-level memory. We have discussed about the average memory access time, and we also try to summarize the memory average access time for a multi-level memory system. So that's all for today's class. I'll see you next time.